Hello, everybody, and thanks for joining our next webinar in the ASRG World series. We're going to give it just a minute and we'll go ahead and get started. I'll apologize ahead of time for my audio if I do sound a little bit like I'm in a glass box. That's because I am. I'm at my office today, so bear with that. You guys aren't here to hear me anyway. You're here to hear our presenter today, and so that's what's important. Okay, so just a couple of points on the ASRG before we get started. This voice you're hearing, I'm Brandon Berry. I am the ASRG Americas coordinator, so I'm responsible for all chapters in North, Central, and South America and their success. My day job, I'm CEO at Block Harbor, an automotive cybersecurity service provider. We've been in business since 2014 doing this kind of work. If you want to reach out to me, contact me at brandonberry@asrg.io. Love to hear from you. What's the ASRG all about? If you're new, we'll share just a few points here. We have three pillars: knowledge, networking, and collaboration. Knowledge, we're interested in creating a knowledge base so that really to reduce the barrier of entry into automotive security. Networking, making sure that people who need to be having conversations can do so, can reach a community around the globe to address challenges in automotive security. And collaboration, so that these parties are working together, everyone from independent researchers to automakers to suppliers, really getting them all in the same room to have a conversation and collaborate with one another. Just a quick survey announcement. We've been running the survey for some time with our partner Cybellum. Go ahead and access this QR code to just give us some insight that we'll share back into the community about some input on vulnerability management. So we're over 6,100 members now with 38 locations worldwide in 20 countries. If you're interested in starting a chapter because there's not one near you and you think there's a automotive security community that you want to cultivate, reach out to us again at hello@asrg.io. We'd love to hear you get started. A few of our upcoming webinars. We have some really exciting ones. We'll be hearing from Privacy for Cars, Ishard, Vector, Fraunhofer, and TÜV Süd. If you want to get up here and present, just reach out to us at cfp@asrg.io. We'd love to get your voice on this world stage. Without further ado, I'm happy to introduce Thomas Leifert from Keysight Technologies. He's going to be talking to us about a new approach to fuzzing. So Thomas, you, just a second, you indeed have the stage. Take it away.
Hello, everybody. As Brendan mentioned, I'm Thomas Leifert. Please excuse my accent. I'm a non-native speaker. I try my best to be understandable to all of you. Today, I would like to talk about wireless vulnerability assessments and a new way in fuzzing that we explored and cultivated. So today we're going to talk about what we call internally Greyhound. Greyhound gives a little hint to those who are familiar with the terms that we're talking about a grey box. And we're going to introduce you to a new fuzzing technology that approaches things slightly different. But before I'm going to go into the details, I'll share why we had the motivation to start this kind of work. And most of you are surely aware that nowadays we have a lot of wireless technologies that are used not only in the Internet of Things space, but also in automotive. And I would like to say the car, the vehicle nowadays is more or less one piece, one pillar of the Internet of Things. Um, Both technologies, Bluetooth and Wi-Fi, are very popular, but especially the modules that's been used in these environments lack very decent security testing. And the potential to run into security pitfalls here is quite big, and um, the standardization in this environment is also lacking, so that um, this leaves room where we thought we need to add something, and we wanted to do something different, because when we now take a look at how fuzzing is usually addressed, so the process of fuzzing is probably familiar to most of you who are dealing with the matter on a day-to-day basis. But just to give an understanding for those who are not doing that on a day-to-day basis, fuzzing means that we need to iterate to um, basically bits and bytes, or even on the signal level, to find flaws in a protocol. To do so, you typically have to create a fuzzing model before you can apply it. So it's not just that you give it a start and end point and then you run through the bits and bytes. You can imagine that this would take quite a long time and would not be very productive, because especially in wireless protocols, you need to follow some kind of um, routine to get a connection established first, or to make something uh, respond to you. So once this model is created, you can start with fuzzing, and then the next step typically is you have to analyze the anomalies and crashes that you identified by doing the fuzzing. Um, from that, you would create your exploits, and finally you can run these in an automated way as a vulnerability assessment. Another way of getting to the automated vulnerability assessments, of course, is studying the known exploits and creating your attempts from there. While I'm saying that, currently we're talking about the roles as a Wi-Fi client, Wi-Fi access points, and Bluetooth Low Energy, while we aim to add Bluetooth Classic to that tool this April. And just to give you something on the horizon, we're intending also to include cellular technologies into this toolbox, that will allow us to apply the same methods on cellular technologies. So what is new on our approach to fuzzing? Well, while we're talking about a gray box, we're talking about a protocol that we already know. And we have taken that and formed a protocol model in form of a state machine, which is then able to fuzz in a more intelligent way. And um, that allows us both to reduce the time in fuzzing, as well as we can easier analyze the anomalies that we find. And the decision making process in the mutations is based on a per cost basis, which allows the packet manipulation in a quite elegant way. Saying that, if we look at the protocol stacks of both Wi-Fi and Bluetooth, and that is, I think, one of the core information you should take away from today, is that we're not fuzzing on a higher layer of the application. We're basically starting on the link layer or on the MAC layer. So we're starting on the layer 2 of the OSI layer model of communication. And that allows us to be independent of the radio link underneath, and also independent of higher layer protocols and uh, details in the model that we need there. Well, what we need to say here is that, of course, this is a combination both of the software we created as well as hardware. So currently we're using some value priced devices that allow us to load a special firmware on it to be able to inject mail form packets and messages on the layer 2. And this for Wi-Fi we use a Ralink dongle, and for BLE we currently use a Nordic semiconductor device. Both devices are in the range of a couple of bucks, so not an hilariously expensive thing. Well, that might change when we go to cellular technologies, because these demand uh, software-defined radios or base station emulators to be implemented. But for Wi-Fi and Bluetooth, these devices are the ones that we support currently. And you see that we're currently only supporting radios in the 2.4 gigahertz range, while the Wi-Fi device can be altered to one that is also supporting 5 gigahertz. And future technology or newer technologies. So currently we have supported ABGN on the Wi-Fi protocols. Future releases will also support wireless LAN, AC, probably AX, and what else is coming. So what are the key benefits of the way that we implement it here? So basically, we do not maintain a database of test cases. We fuzz with an initial set of random values that's based on the probabilities. And the configuration is really down to selecting the device that you would like to apply the fuzzing to. So when you set up an access point, you can select the client that you would like to fuzz, or vice versa. If you set up the fuzzing tool as the client, you can fuzz the access point you're attaching to, and the same is true for the Bluetooth devices. So presets to get started with fuzzing is really easy, and I will share a little video where a colleague of mine is sharing his screen and showing how this has been actually applied to a device, and how that looks like. One big benefit for the ability of testing down to the link layers, that rather than sitting on the application layers or just slightly underneath, is that most fuzzing tools that you see on the market, both open source as well as commercial ones, are not able to do that. And this gives us logs and a deep insight in the security layers that are in between the second layer, so the MAC layer or the link layer, up to the application layer, rather than just concentrating on the layers above. Well, you see that configurability is currently grayed out. That is a feature that is going to be released soon. So that is on the things that we're going to add, allowing you to alter the protocol model, the state machine model that we introduced here. But on the other hand, we have a REST API integrated that allows to seamlessly integrate our Greyhound solution in other environments and automate testing as we see a dedicated need for more testing, more automated testing, but that is a topic for another discussion. So when we look at Wi-Fi, there's 3 new vulnerabilities that we uncovered when we tested our Greyhound solution, and they are both found in the quite popular ESP A2 ESP66 and the ESP32, which are IoT modules. They're not as often seen in vehicles these days, but they're very popular devices, and that the chips that are used here might also be used in automotive environments. And I will share a link later in the presentation. You can follow these findings that we have listed, and most of them are crashes. So you see an anomaly, you see the device crashing, probably not able to recover without power cycling from that crash. And let me share a little bit more in the details how that works on Wi-Fi. So the first one that I showed in the screen before is the setup is like following. We're using a raw-link dongle as the access point. Um, the reason for that one is because the chipset allows us to inject the packets in that one, and the ESP is our target device that we have in a role as the station to the access point. And first, you start a normal negotiation between the devices, the the four-way handshake between the devices, and then once connections are established, we go into a probe request, and then we send in a mail form frame, and that basically breaks the device into a crash, and you need to power cycle that. Well, that might not only be impressive because these were completely new, unknown so far, and that were findings that were found in a few minutes. And I will show that one later on in that little demo, and you can see how fast that works. And again, it's not a tailored exploit that we run in the demo. It's definitely the fuzzing machine running to the um, mutations and finding this crash. So let's have a look at Bluetooth. On Bluetooth, we have a much larger set of findings. Some of them are known as swine tooth. Swine tooth is a family of vulnerabilities, and all of them were discovered using the Greyhound technology. And this affects about 480 products of systems on a chip. And you see there's probably a good chance that in your device is one of these chips being used. The links in this presentation gives you all the details to the findings. In the table, I just listed a short description of what happens. So this is just a abbreviation of what actually happens in the things. And I will share one of the Bluetooth low energy attempts. So we're going to run a fuzzing versus an audio headset, quite actual one from Sony, and that will go into this LLID deadlock because it's based on a Cypress chipset and an XP chipset. And you will see that the audio will drop out and takes a few seconds to reboot the device to get audio back. And actually, that's the headset I'm currently using. So let's have a look on the setup here. So target device, okay, this is the development chipset, but basically the chipset that's been used in that headset is the target, and connected to the computer with the Greyhound software on it is the Nordic Semiconductor BLE dongle. And the BLE dongle is configured as the central, as the master, while the headset for sure is the peripheral, is the slave. And while the data channel selection channel connection is being established, there is an invalid version request to the device, which completely locks it in. And basically, the only way to get out of that is rebooting it. Um, Another one I would like to share some details on is a link layer overflow, and it's a very similar point where this happens in that protocol that's been implemented, but here the length of the LL length is being changed. So you see there is a padded version request, and that will make the link layer overflow. And you can see padding sitting down here to 242 bytes, which will run into an overflow. And as most of you will know, an overflow is what a hacker probably is looking for, because that might allow him to introduce his own software, his own bits and bytes into a device. Well, the third one is as a zero LTK installation, and it basically affects all products using telling chips. With the support for secure connections. And especially when you're talking about a secure connection, you don't expect that to happen. And actually, the central, in this case, again, the dongle acts as the central, as the master station, skips the secure connection pairing procedure, and just starts the encryption by sending an encryption request. And interestingly, the client accepts that request without negotiating the details of the encryption. So basically, the encryption is worth not a penny. So are there other tools that could do that, could compete with what we have implemented here? And we haven't found any open source or commercial tool that could compete with the number of findings, nor with the speed that we achieve by implementing the protocol state machine and set up directly on layer 2 um, of the protocol, rather than going to the higher layer levels. Um, Especially the findings on Bluetooth are numerous, and as I just showed with the telling device, even bypassing encryption is a very severe finding on it. So what have been achieved is that we have completely implemented a new way to fuzzing. Um, it has raised some alerts in regulatory agencies, and it has, of course, caused some noise in the news channels, as you can see on the right. But it also allowed us to file to patents on the methodology of finding these zero-day vulnerabilities in, well, Internet of Things devices, what applies to the automotive world in full breadth, of course. Um, just to share a little bit of the details, what we can do right now with this. So on Bluetooth Low Energy, we can configure both as peripheral, advertiser, link slave, GET server. Um, what we address here is the link layer. Every field of the link layer can be manipulated. L2CAP, logical link control and adaption protocol, um, secure manager protocol. So that means all BLE pairing modes are supported, except for the out-of-band ones. Attribute protocol, and very important, GATT, generic attribute profile, which is present in almost all Bluetooth Low Energy devices. On Wi-Fi, we have the ability of configuring it as both as access points or as clients, and we can work down from Mac, airport security. WPA2. Recently, I had a question regarding WPA3. It's in the make. It's not yet there. We're working on that. For sure, that is a very interesting topic with this new security encryption being implemented in newer devices and new software releases. So we're working hard on that. And as I mentioned already, we're currently supporting BGN. At least that's what we tested. But we sure as from the same family of chipsets, there are chipsets that support ABGN and AC, that we can support them very soon. So that was my presentation part, but I don't want to leave you without showing you how easy it is to use it, how it works, to give you a sneak look under the bonnet of that thing, and allow you to have a sneak preview what we have in mind here. So let me switch over to my other screen, and let me start. And as I mentioned before, that was done as a recording because it would turn off my audio at a certain point in time. And actually, what you can see here is the predefined interfaces, so the API of the device that we can call. Actually, we have implemented Greyhound in our own solutions in a way that we have it Dockerized, so we have put it in a container. The only things that we hand over to the container is basically the configuration for the device.
Hey
And
Thomas, I think we can still see your presentation if you're trying to show something else.
I just hear that I'm sharing the wrong screen. Bear with me for a second, and let me share the right screen. So, okay, sorry for that. And I hope we're good to go now. So what you see here is on the right side, this is where we have the API, and we're just configuring the device as an access point. We give it an SSID, we give it a password, we select a channel, and we can configure some other settings on the security. And then basically we send that to the container, and on the left you can see the start of the application, and you can see it's doing an authentication request, and you see the highlighted fuzzing input, so the highlighted packets, and you see them coming through pretty quickly. And go into, so it'll take a few seconds, but then we'll go into an anomaly. But to show you another interface to that, we have also a graphical interface where you can see the state machine in the background working and where we are in the protocol at the moment. So you can see the different associations and authentication requests, and logging of the data. So, and it's a few more seconds while we see the anomalies. And you see the orange box in the lower right. So we found an anomaly, and that's been logged in a folder. And we'll have a look at that later to see what exactly happened and where it happened. And there's another one during the authentication request. Okay. So now we're going to have a look at the logs that we got from that. So the fuzzer has stopped. We can go into the results folder, and we can open the logs, and that was the device that we first, and we're also recording the PCAP files for Wireshark, so we can analyze that. But for the first step, we're going into the CSV file, and the CSV file gives us an important information. Colleague will open that now in a text document. It's not a very long list. So basically, what you see here is that the anomaly happened in the 18th iteration of the Fuzzing engine, and that basically directly points us to where it happened, rather than just recording a few lines ahead of the anomaly, and then you need to scroll to lengthy files to find this. With this information, we can go right um, into the PCAP files in Wireshark and open them. And basically, you can see all the messages, all details, everything from layer 2 up for the highest layer has been recorded here, and allows us to have a look into that. Well, there's another anomaly we found. We're going to have a look at that, and that was the one I showed before, and that's basically where after the four-way handshake, we inserted a mail-formed package, and that's so. And then you see here, this is an incorrect response on what the fuzzer sends in, and it, it ends up here. So that is the results that you get from this tool, and how you can work with that, and pointing pretty precisely to where it happened and what happened is, I think, one of the big benefits in that. Well, the next thing we will see is an example for BLE, and BLE will actually work in a similar configuration way, but in this case, we're not setting up an access point. We rather connect to the device and use the MAC address, so the unique UI identifier of device, to connect to it. So for that, we're going to call up the Bluetooth API, and so that will be the LLID deadlock that I showed in the presentation before. and you see the target device's MAC address is set up in the configuration, and colleague is just showing this is from where he discovered the device. So he's actually connected to that device, and he now starts it, and it takes about 40 seconds, and his device will go into this LLID deadlock, and you can see this is the scan results. So dot is vulnerable. It already found it, so it's just a few seconds. Receive the packet with the LID field cleared, then both devices simply. So this is the complete description of what happened right now, and now he needs to restart his device to come back and talk again to us. So I hope this was interesting, and shows how fuzzing can be addressed differently from previous attempts on other ways, and gives you ideas what can be achieved by thinking slightly different, slightly out of the box here. Um, I would say thank you for your interest, and I would like to open the discussion right now.
So Thomas, thanks a bunch for this presentation. Really love how you dove into just some of the low-level details of what we're talking about here. To reiterate a few key points from your presentation, fuzzing is a technique of sending randomized data to inputs into a system to try and uncover some input that causes an anomaly. What you guys are doing at Keysight is taking some of the lower layers in the OSI model and fuzzing protocols in those layers rather than fuzzing at the application layer.
Precise.
Understood. So that's really cool. I mean, because when we think about a lot of the fuzzing tools out there, and I don't mean to get too deep into the weeds here, but Redamza as an example, which is a fuzzing library, think of it, where you give it some input, it generates a randomized output, you pass that into an API, you observe the API's response. A lot of these, to your point, are application layer fuzzing tools. What you're talking about, lower layer networking with these wireless protocols, is really challenging. It's a lot less accessible because you may need specific tools to do it. So just to relay a few of the questions from the audience that I think you'll have some insight on. One is, how are you guys monitoring the target here? One of the biggest challenges in fuzzing is what do you key off of to determine that an anomaly has happened? And so the question is, you're talking about BLE, you're talking about fuzzing Wi-Fi. What sensors do you have to detect anomalies in the target, and how are you doing that monitoring?
Yeah, I think that's a very good question. And actually, that brings me back to one of my first slides where I showed that basically we have a state machine of the protocol. And having that state machine basically allows us to predict what would be the next reply that we would expect. And if that reply is not coming within in a certain time frame, we for sure know that we have found something. So that is the first mechanism that we use to to find something. And then with the logs taken, might it be Wireshark or other tools, allow us then to analyze exactly what happens. So one of the big benefits here with the implemented state machine is that if you would go for a classic fuzzing tool, you would probably need to have very deep knowledge of the protocol and how that would behave. And that is what we have implemented here. So I myself started my career in wireless communications, so I'm doing that for more than 20 years. So I would say I'm almost familiar with wireless protocols, but I know that they can be a big challenge for people who are not sleeping with Etsy documents under their pillow, and they're not straightforward either. So having this put into the state machine is one of the major tasks that we have taken to achieve that, and that allows us to find things, and then with the logs we can nail it down to the line, and basically from there it's easy for somebody to analyze his own code down to the line of code where it happens. Um, and I think that's making things much faster than in the past and with other tools.
So I think I understand. You're saying that essentially the protocols were codified into a state machine, and any deviation from the expected behavior in that state machine, a set of predefined states, is logged as an anomaly.
Exactly.
So, the audience is asking this question around these anomalies. Let's take an example that the audience is bringing up. Um, what if say there was no response for a given request? Can you just maybe illustrate or talk through how that would be logged as an anomaly in the state machine? Meaning, say the target is hanging on that request because something is going wrong. Definitely an anomaly. We can agree upon that. So yeah, maybe can you just walk through that example?
Yeah, exactly. So what we're doing is we're and that is what my colleague showed in the demo in that CSV file is we're logging also the mutations that we're applying. So basically, we exactly pointed to in which mutation the unresponsiveness happened, and that means. From that point on, we know exactly the point in time and in which mutation it happened. With that, we can go into the log files and point it directly to that status, and then we can see what happened before and after, if there's something after it. If it's in the dat log, there is not much to see anymore. So you see it end there, but you see exactly, for instance, if we take the example of the four-way handshake, where then the mail form packet was sent to the device, where it completely hung up. Um, you see that mail form package coming in, and from then on, the device didn't respond it. And that's basically the information you need to point it. If you were the developer of that software on the Bluetooth device, um, you would have a hint where in your protocol or in your setup you would need to find that, because you can pass that package treatment in your code, and that would tell you what went wrong.
Got it. So you log this information and the corresponding anomaly, so that in post analysis you can trace it down in your own code.
Yeah.
Okay, so just to maybe dive a little bit deeper into this, um, the approach to fuzzing is with your presentation here is really focused on deviations from the protocol, if you will, deviations from an expected response. Does this tool have any ability to ingest additional sensors that maybe go beyond that state machine of the protocol? In other words, could you monitor, some input based on device behavior or something like that you may not detect? In other words, the device may respond as the protocol defines, as the state machine expects, but there may be some bigger issues going on in the device itself. And I think a Stack Overflow is a good example of that. That maybe the chip on the target keeps functioning and maybe responds properly, but that overflow maybe causes application layer errors. So Thomas, can you guys like take additional inputs that go beyond the state machine?
Yeah, that is why we implemented a REST API that allows us to interact with other instances. So that might be used for automating the process of configuring it, but that also might be used for um, giving additional inputs into the logging, which allows us to align these happenings that you monitored in a different way. Let's say you have an LED on your device just as a simple task, and you monitor the LED. Um, However, with a camera or with an just testing for a voltage change, when that LED comes up, we could trigger that and align it with what happened in the state machine, and hence we would know on which iteration it happened, and we can point it directly into the logs as well.
Okay, and I think I got that. Meaning, in essence, you can add additional states into the state machine, like an LED turning on, that
Yeah, that
need to be a part of that process. And if you don't get the right state, let's just say the LED goes from green to red based on a Stack Overflow, as a visual example, then you can fail out and log that instance in the fuzzing tool.
Yeah, but actually, there's two methodologies. One is just like a trigger signal that can be recorded and put into the REST API. The other thing is, as you mentioned, we can go into the state machine and at a different state, we can alter the state machine. That was grayed out on my presentation. As I said, this is not yet enabled to customers because we're still working on that to make it easier to do that, because you can imagine a state machine for a protocol isn't easy to read if you haven't got a deep understanding of the um, whole beast, I would say. If you just want to add in a tiny little thing, so we're trying to improve the interface in a way that you do not need to deep dive to add those kind of things.
Okay, so it's some combination of the ability to implement additional states, but also external triggers into this
Correct.
process.
Yeah.
That makes a lot of sense, Thomas. One of the when we think about fuzzing, there are, I think, two big challenges. One is, what is an anomaly? How in the world do you detect an anomaly? What I like about this presentation, what you guys are working on, is you're saying, well, one of the things that is under our control is that we can analyze the response with respect to the protocol and expected behavior for that protocol. Because maybe a little bit of a delayed response, as an example, maybe an indication, and maybe that falls out of the bounds of the protocol spec. So that's one of the huge challenges in fuzzing, is trying to understand what is an anomaly, because otherwise you're just sending random input and you're kind of hoping that that anomaly makes itself obvious. The device shuts down or something, or uh, yeah. I mean, that's a huge challenge. Is, yes, it's easy to fuzz, but how do you make fuzzing useful?
That's the point. How do you make your findings useful if you have findings? Sometimes it's even you don't have the findings because you didn't observe that something happened on the screen or on the device itself because you do not have the right access to what happened. So especially if you're not talking about a white box where you have access to the code and debug interfaces, if you're sitting in front of a gray box, you do not know everything, and the harder it gets to find this.
So Thomas, I'm going to finish off this question based on that difference between white box and gray box. So we talked a little bit about different states in the state machine, talked about external triggers. Let's say it is white box. Let's say we do have the ability to really do anything we want in the target. Is there anything additional you can say about how that would change the fuzzing of that target? I mean, is it just that you can have more triggers that maybe go into the code execution stack, or is there something else that maybe comes to mind?
Well, if you're talking about a white box, you probably have a good idea, if not a decent knowledge about what should happen or how a device should behave, which makes fuzzing in general more easy. Um, because you know the expected behavior. Still, even if you know the expected behavior, it might be difficult to observe it because fuzzing might not lead to a very obvious thing. But having a white box means I have more tools available to look at that, no matter if you use our tool or other tools. While especially a gray box is a challenge because you do not have this knowledge, and that makes it levels more complicated to do so. And that is where the state machine on the layer 2 comes into play, and in full force, where you can see an expected behavior of the protocol. And if that's absent, a protocol is basically corrupt. That means it's not, and that is one of the big differences on Bluetooth and Wi-Fi. On cellular technologies, there are tests to test the protocol. So there are protocol conformance tests. So there's like all kinds of, well, this is a positive test. The protocol conformance test is a positive test. That means you test if the protocol is responding properly to all valid requests from the protocol. While fuzzing is aiming for the opposite of it, we're trying to achieve a negative test of a protocol. And as for Wi-Fi and Bluetooth, there are no protocol tests in that depth that we see them in cellular. It's good to know that the negative test is giving you the results in a similar depth that you need it. And I think that is important to understand. Bluetooth, you can create your own stack, you can create your own protocol. Well, you could do that on a cellular device as well, but you wouldn't get past the official regulations if you do that on a product. But anybody can buy a Bluetooth SDK and create his own Bluetooth protocol. Question is if that protocol is good. And examples for that, like Blue SDK and so on, are well known that they are exploitable. Um, so I think this is not to underestimate.
So Thomas, fuzzing is a technique, and you guys are applying that technique to low layers for wireless technology. Does this tool move up into different layers? I'm thinking with our audience here, we're all really concerned about other aspects of the vehicle as well, which is like CAN bus, or automotive Ethernet, or maybe protocols within V2X. Is there? I mean, can you comment about the extendability of this tool into application layer and other layers within communications?
Yes, well, we started with Wi-Fi and Bluetooth for a reason. As I mentioned, there's many devices out there, and of course, all wireless interfaces are of special interest because typically you do not need to have physical access to a device. It's good enough to be close to it in case of Bluetooth, even further away with Wi-Fi, and you can be on quite large distances in cellular technologies. But when we're talking automotive, there's for sure automotive Ethernet and most common CAN bus of interest. And we're also looking in possibilities to apply this here. A state machine of a CAN bus protocol. So rather than just taking a DBC file, creating a state machine of that would be very interesting and probably give you another level of insight than you can achieve in any other method now.
So how easy is this to use in terms of creating a state machine? Meaning, uh, is it really that kind of usable in that, say, I did want to fuzz can and I did have a method for producing a message and then going through different states that I would expect based on, sure, a DBC file or whatever else. Um, is it really, is that the biggest task here from a usability standpoint, is generating that state machine so that you can essentially define anything outside of that state machine as anomalous behavior for a new protocol?
For sure, the state machine is the biggest workload in that environment. So that is why we create that on standardized protocols. Well, and that I think is one of the things why we didn't start with CAN bus as you might have expected. As CAN bus is not very standardized except for OBD2 debug protocols. This is more difficult. And to create a state machine, of course, you need a description of how that protocol should work. A DBC file is not exactly describing what happens. It just describes the commands. So it basically tells you, well, this command will turn on your headlights. This one will tell you the speed, but it does not tell you um, how the machine should react if you send a dedicated sequence in detail. And that is where the problem probably is. While Bluetooth and Wi-Fi are documented standards, so this is how devices are standardized to be able to communicate with each other. Um, so that means when we go back to the CAN bus example, if you have an understanding of how the CAN bus would function, so e.g. you would be sitting in front of a white box, you can create that state machine for sure. If you don't have a clue about that, it might be more difficult or even impossible.
Got it. So Thomas, I say, I kind of mentioned that I see two big challenges in fuzzing, and both of these affect the quality of fuzzing. Um, One is determining what's an anomaly, because if you don't know, then you don't know if that fuzz input generated an anomaly. The second in my mind is that fuzzing is a technique that you can do forever, really. Because unless you really truly exhausted every possible randomized input, you can do it for a long time. So Thomas, how do you think about time of fuzzing if you're using randomization? Do you let this go on for just 2 weeks before you take a look at the logs? I guess, what's your insight and experience on that?
No, no, exactly. That is a valid point. In the way you describe fuzzing, you would probably need to wait for an extended period of time. Um, the way we implemented it is one of the things is that the state machine can guide the fuzzing engine on what kind of mutations are um, meaningful. So that means there is an algorithm inside that, well, it's called on a per cost basis calculation, and that means what influence could be achieved by that mutation, and that is where the speed advantage comes from. So first of all, finding an anomaly is one thing. The other one is how to alter the mutations through and select the right values. And starting from a random value is one thing, but limiting the mutations to ones that can have an effect is the other thing. And that, I think, makes what makes the Greyhound approach so different to classical way of fuzzing.
Well, and that kind of leads into the next question. Is you're right? You know, the way I described it is you're truly using randomization to provide the input that you're going to put into the system. Um, However, fuzzing becomes much more valuable if it's done intelligently. Meaning you don't truly want to take a random input. You want to take an input that modifies based on known weaknesses, and that reduces the space in which you're fuzzing. You know, to take an API as an example, we all know that APIs tend to have a common, you know, OWASP top 10 list of vulnerabilities that really just are caused by the underlying implementations. Where, as an example, SQL injection may be one of those types of vulnerabilities. And so when we're fuzzing an API, we're thinking about, well, we shouldn't start with random data. We should start with maybe a baseline of SQL data that we then iterate based upon that. So Thomas, I think your point maybe was resonating that with a little bit, insofar as you're starting with a baseline, you're using intelligence or an algorithm to try and stay within the bounds of that space so that you're not fuzzing an infinite space.
Yeah, exactly. And there's another side of Greyhound, and we call it Greyhawk. And basically, that is taking known exploits and run them through the fuzzing engine, which is another way that we have implemented to look for vulnerabilities on an unknown device. So, like all the exploits that we know of for Wi-Fi and Bluetooth have gone into Greyhawk, and that allows basically the fuzzing engine to run to these dedicated starting points and go from there. And that, and again, is a method of limiting the amount of time that you would invest.
Ah, I see. And so what that becomes is a combination of a vulnerability scanner and a fuzzer, where you're taking known payloads, and then maybe you start with that known payload just to make sure that that is not indeed vulnerable to the same exact thing. But you're saying, hey, if this caused a vulnerability, what if we tweak some part of that payload and submit that? Does that as well? And so you're taking that as your baseline and applying some degree of randomization to try and find a vulnerability along the same vein. Is that right, Thomas?
Exactly. But as we wanted to talk about a new approach to fuzzing, I did kept that out of the presentation. But basically, yes, there's Greyhawk. That is the other side of Greyhound, which is definitely a vulnerability scanner based on known exploits, and it uses the same engine, the same environment, but it starts with preloaded sets.
Well, Thomas, I'm pretty excited about this tool set because it reminds me of a tool called a chip whisperer, where you're creating a tool and a usable tool so that people can, it lowers the barrier of entry into, say, hardware hacking in the case of chip whisper, and attacks like side channel attacks, or power glitching or power analysis. And in this case, what I kind of took away from this is that it removes a lot of the protocol expertise required in order for a security person to come in and utilize that fuzzer to find vulnerabilities in it. So I really appreciate this tool from that standpoint, in that you guys at Keysight are using your protocol knowledge to make fuzzing into these lower layer protocols more accessible. So Thomas, thank you for this presentation. I really appreciate it. I appreciate what you guys are doing. You're always welcome back here on the ASRG. Is there anything you want to leave the audience with before we close out?
I would say thank you for your interest. I think it was a tough part for those who are not familiar with all those protocol wordings, but I think it should show that there are ways where fuzzing can be made more accessible, even for those who are not on a day-to-day basis working on that. And I think that's one of the very valuable points in it, that we take in our knowledge, our expertise in wireless, and put that into it. And we will work to have more of that. As I mentioned, we're working on cellulars, and we're also looking, of course, into CAN bus and other protocols. Everything around the automotive environment is of interest for us here, and but as I said, there are of course limitations in creating a state machine. It definitely needs deep knowledge to create one. It's easier to alter one that you have in front of you. So that is why we have the ability, or why we open up the ability to alter the state machine. But for sure, creating one from scratch isn't a thing that you would do between breakfast and lunch. Thanks so much. I really appreciate ASRG and being able to talk here. It's an honor, and I hope it was useful for some of the audience, or most of the audience. And thanks for staying online. And who's interested in more details, please contact us. We can help you, or contact Brandon. He can guide you on the right contacts here. Thank you very much, and goodbye for today.
Okay, and those of you joining us in this ASRG World webinar, thank you for tuning in. Again, stay tuned for these upcoming webinars. We have a lot of really exciting ones coming up. And so with that said, we'll go ahead and close out. Again, you guys, everyone take care and stay safe, and we'll see you on the next one. Okay, thanks everyone.